Okay, ladies and gentlemen, welcome back to the last week of your favorite class. All right, until the fall when you're enrolled in 3005 or 429, in which case that will be your favorite class with me. Okay. Right, announcements. I finally finished grading all your simulations. It kind of took me a while, so apologies. You know, it wasn't my normal one-day turnaround, but those simulations are long, kind of a lot to grade there. So apologies that it took a little longer than normal there. But should have your grade now. The only thing left now that you have for grades of the class is homework number 6, which you just turned in, and I'll try to grade, here tonight and tomorrow, and then your last exam for the class, which is exam number 3. So pretty much done with everything for this class at this point if you turned in your homework today, except for the exam, which will take place on Thursday. So the exam will be just like all the other exams, where come a couple minutes early, I'll post it on Blackboard, you'll take a look at it and do everything by hand and send it to me electronically at the end. All right, so that's that. Guys did a really great job this quarter. Everyone turned in the simulation, everyone's turning in all the homeworks, like no one's dropped the class. It's like really proud of you guys considering all the like BS that we've had to deal with here. Okay, so keep that stuff up. All right. That's it for the class. What we're gonna do this week, today and tomorrow, practice problems from the document that I handed out is on Blackboard. So your exam 3 practice problems, what we're gonna go over today and tomorrow. Today we'll focus on momentum stuff, and tomorrow we'll do linkages and gear stuff. All right. So that's what we're doing today. Thursday, you got your test. Friday, nothing. All right, no obligation. So nothing during this time on Friday. Any questions before we dive in on review problems in the chat? No questions. Sweet. All right. What do we think of the meme today? The effort of many scientists. One of the greatest technological challenges, the launching of a rocket, all to deliver internet to Billy. The Earth is flat. Oh man, love the little like sailboat falling off the edge of his flat Earth T-shirt. Also, subtle there by the author of the comic. Very funny. People looking at their cell phone saying the Earth is flat when it requires a satellite in geosynchronous orbit to deliver you GPS and your crap on your phone. It's ridiculous. Okay, well, there you go. The Earth is flat. Right. If you believe that, you don't belong in this. You're not smart enough for this class. All right, away we go with our practice problems. So as a reminder, I did post these practice problems to Blackboard, and it's a document that looks something like this. All right, your exam 3 practice problems. There's a couple problems on impulse and momentum, 1 on impact, 2 on impact here, and then a couple on linkages and a couple on gearing systems. All right, so you can kind of see these and go through all these and as a sort of refresher. I want to start with a very simple problem on impulse and momentum. We'll start here with number 1. Just want to remind you about radius of gyration, and remind you some of the things that we talked about for conservation of momentum. So let's I wonder if I could just copy and paste this right to my board here. I don't even know. Can I copy and paste right to OneNote? I guess we're gonna find out. Ready? Moment of truth. Yeah. What? That's not where I wanted to go. Stupid technology and whatnot, jigger digger. Oh, baby. All right, how about that? Can you deal with that? Wish I could make the text a little bit bigger. Can I do that? Oh, I can. Look at that. Dang. Ain't give me a PhD for nothing, I tell you what. All right. So here we go. We got a 60 kilogram wheel, radius of gyration. Here I give the variable little k. About its center, 300 millimeters. Remember that radius of gyration is related to mass moment inertia with this I equals mk squared. It's part of the reason I want to go through this problem. If it's subject to a moment of, here, a time-changing moment, 3t squared Newton meters, where t is in seconds, determine the angular velocity of the wheel after 4 seconds if the wheel begins at rest. All right. So kind of the picture you should have in your mind. You've got this wheel on a rotating shaft. Pictionary skills still subpar. All right. You got this sort of wheel on a rotating shaft, and it's moving around here with some moment that is 3t squared. All right. The mass of this guy is 60 kilograms. And we're told the radius of gyration, this K, is 300 millimeters. All right. Hopefully you talked about radius of gyration in your 2002 class. Briefly, I will mention that radius of gyration is a physical interpretation of where you would have to put all the mass of an object at a distance away from a rotating axis to give you the same mass moment of inertia. If that means nothing to you, don't worry about it. Just understand that the relationship here is I is mk squared. All right. So if that's the situation, I is mk squared, then here the mass moment of inertia of this particular disk that's kind of like spinning around this axis is equal to 60 kilograms times the radius of gyration. I'll do it in meters, 0.3 meters squared. I did that conversion in my head. Thank you very much. And then your mass moment of inertia here, 5.4 kilogram meters squared. Don't forget your units. Units. 5.4 football fields. Rawr. All right, 5.4 kilogram meters squared. So there's your mass moment of inertia. And why is that important for this problem? Well, this is a conservation of momentum problem. So let's jive our memories and we'll do conservation of momentum. And remember, our conservation of momentum equation looks something like the summation of the angular momentum of object in state number 1 plus the integral of the moment impulses that are applied over time equals the summation of the angular momentums of that object in state number 2. All right, this is our general conservation of momentum equation. Must be done about a fixed point or about center of gravity. And don't you forget it. All right. So we're told that this thing starts from rest. You could make a diagram here if you want. I'm not going to make the diagram. I already made the picture. All right. It's not really that complicated of a problem. All right. So here we're told that this thing starts from rest, so it's not spinning with any angular motion about this particular axis to start with. So we have no initial angular momentum. Here the term, which is the integral of the moment dt, is the integral of the moment which we're given as a function of time. So this is our impulsive moment here, given in terms of time. So maybe this is some flywheel being spun up by some motor, and there's some initial drive of the motor where it takes a little bit of time to get going. All right, so let's say that this is 3t squared. And in this particular problem, we're told that it starts from rest at time t0. We're interested in what happens after 4 seconds. So we'll make our limits here 0 to 4 seconds, integrating over time dt. This is going to be equal to the angular momentum of my flywheel in condition number 2, which we know from the definition of angular momentum. This is just simply going to be ig omega, or if you want to call this omega 2, because this is the angular velocity in condition number 2, that's fine. I'm just going to leave it as omega as we go forward. All right. Let's perform this integration. So easy a caveman could do it. You're going to end up with something like t cubed from bounds of 0 to 4 equals to, I already calculated my mass moment of inertia, 5.4 kilogram meter squared, times my angular velocity omega. All right, 4 to the third power, it's going to be 64, equals 5.4 times omega. End up here with omega equal to 11.9 radians per second. So there you go. Brush your shoulders off. All right, ladies and gentlemen, brush off those shoulders. Just getting you reacquainted or reintroduced to conservation of angular momentum, right? So that's your reintroduction, talking a little bit about your radius of gyration, just so that doesn't escape your mind and escape your memory, and getting you back on track with conservation of momentum. All right, so that was sort of a little warm up. That was our little jaunt around the field. Now we're ready to play the game. All right. And when we play the game, we're going to move on to a little bit more complicated of a problem. One, and I think probably the most complicated problem on this discussion about impact and momentum, impulse and momentum, is this problem here. And this is the problem with like the pendulum, and a bullet is striking this particular pendulum. And the reason this problem is particularly complicated is you have multiple components in the pendulum. You got the rod, you got the disc, you've got this bullet that's hitting it, and the bullet is kind of sticking to the pendulum. How do we deal with that? So I particularly like this problem. There's a lot here. There's a lot of aspects, and it's just good to sort of brush off the shoulders and go through this problem, okay? So you got a 10-gram bullet, velocity of 800 meters per second, fired into the edge of a 5-kilogram disc. Determine the angular velocity of the disc just after the bullet becomes embedded into the disc. So the bullet embeds into the disc. This is important. It does not rebound off. It becomes one with the disc in a very Buddhist type way. Become one with the disc. All right. The rod AB has a mass of 3 kilograms. All right. So let's go through this problem. I'm going to copy the picture over, and I'll copy the relevant information over to the screen here. So this is problem number 4 from review. And let me copy this image over here. All right. A couple of things that we're told. This guy has the mass of the disc. I'll call M sub D is equal to 5 kilograms. All right. Mass of the bullet, I'll say, is M little b. Here is 10 grams, which is 0.01 kilograms. Again, did that conversion in my head. I know you're proud of me. Grams to kilograms, that's easy. Feet to yards, feet to miles, no thank you. Mass of the rod here, this guy we're told is 3 kilograms, and starts at rest. And the velocity of the bullet coming in, obviously, is given, so I'll say that this is V sub B, 800 meters per second. All right, I think that's about all we really have as given information. We want to find omega right after bullet embeds. Does embed have 1D or 2? The world will never know. Okay, so let's remind ourselves with conservation of momentum problems, if we're doing conservation of angular momentum, we can either do our analysis about a fixed point or about the center of gravity. Let's hold off just a second and make that decision after we do our impulse momentum diagrams. So remember, conservation of angular momentum, you'll want to do an impulse momentum diagram, so let's do that first. All right, these impulse momentum diagrams, you've got some initial momentum, the impulses that occur, and the final momentum. So here we have initial momentum. We've got the impulses. And we have the final momentum. Bam. All right. Again, put my Pictionary skills to the test. All right, so here's point A kind of at the top, and we've got this slender rod and then a disc kind of at the bottom, all the way back up. Bullet coming in on the left-hand side here, about to strike this disc. The bullet coming in, that's going to have a linear momentum, which looks like mass of the bullet, velocity of the bullet, state number 1. So this is MB_VB1. That's really the only momentum we have in state number 1. It's just the bullet about to strike this pendulum because the pendulum's at rest, right? Next, we have to look at our impulses which are occurring. Okay, our impulses, again, we have up here, this is point A. And again, the bullet now kind of embeds or gets stuck in the side of this particular pendulum. So what happens in this situation is the bullet is striking the disc kind of at the bottom. but it's becoming embedded. So whatever forces are transferred between the bullet and the disc are not external forces. They're internal to the system. So we do not have to draw them as impulses on this particular part of the problem because the forces that are transferred are internal to the system. All we really have to concern ourselves with is the impulses that happen here at point A when we separate the pin. So we have a force here at A in the x direction, and we have an impulsive force here at A in the y direction. And those really are the only impulsive forces that are of any importance in this particular part of the problem. All right. Now, final momentum, this is where it gets cray-cray. All right, this is where it gets crazy. Crazy like a fox. All right, so this guy has got a lot of craziness going on. At this point, the bullet is embedded, and the rod, the disc, and the bullet all now have fixed axis rotation about point A up here. The rod has fixed axis rotation about A, the disc has fixed axis rotation about A because it's attached to the rod, and the bullet now, which is attached to the disc and the rod, is also got some motion about point A. So all three of these like objects, the bullet, the disc, and the rod, all fixed axis rotation about A. All right, so all three of those objects now have fixed axis rotation about A. Why is that important? Well, because we're going to look at the centers of gravities of all of the three different objects. So here, this is the center of gravity of the rod. Here, this is the center of gravity of the disc. And here, obviously, this is the center of gravity of the bullet. I mean, the bullet doesn't really have any volume, so obviously there's the bullet that's located there. All right. Now, when the bullet strikes the pendulum, it's going to get the pendulum to sort of move in this counterclockwise fashion. So when that occurs, the center of gravity of the rod is going to get some linear momentum because of this motion around this like circular path that's going to occur about point A. So we need to have velocity that's tangent to that circular path, which is just going to be to the right here. And I'll call this mass of the rod, velocity at the center of gravity of the rod in condition number 2. So MR VGR2. A lot of like variables here, or subscripts, but that's the general idea. Same sort of concept is going to happen here with the disc. The disc is going to have a circular pattern. It's going to have fixed axis rotation about point A in that sort of path. All right, so the velocity, the center of gravity of the disc is going to be to the right with mass of the disc, velocity at the center of gravity of the disc, state number 2. The tricky bit is the bullet. And the bullet is not directly below point A. It's offset to the left slightly. So what's going to happen with the bullet is it's going to follow a tangential circular path about point A. But what happens here is that the distance from A to the bullet looks something like this. And because this particular line is not perfectly vertical, the velocity of that bullet, since it's on a circular path, is not going to be purely horizontal. People want to make the error and say that the velocity of the bullet is going to the right there. No, that is incorrect. Since the bullet's stuck in on this particular rigid body now, we have to accent the fact that it is offset from the left, knowing that this is sort of perpendicular here, and it's going to have velocity in this sort of general direction here, right? So it's not exactly horizontal. There's some angle because this bullet is sort of on this circular path now. Don't forget that, all right? That's probably going to come up on Thursday, right? So here we have some offset, mass of the bullet, velocity of the bullet, state number 2. Right? Now, aside from these linear components that I've drawn, there are also going to be angular momentum components associated with each of these pieces. Those guys are a little easier to understand. Here we have something like the mass moment of inertia at the center of gravity of the rod times the angular velocity of the rod. We're going to have here for the disk something like mass moment inertia at the center of gravity of the disk times the angular velocity of the disk. So we have 5 components of angular momentum on the right-hand side there. Yikes town. Angular momentum associated with linear motion of the rod, linear motion of the disk, linear motion of the bullet, angular motion of the rod, and angular motion of the disk. Yikes town. A lot of crap. But you can do it. We can tackle it. Can do conservation of momentum about either a fixed point or center of gravity. All right. Let's make an intelligent choice here about which point we would like to select to do our conservation of angular momentum. If I wanted to do it, let's say, about the center of gravity, I would have to find the center of gravity. Okay, I got a disc, I got a rod, and I got a bullet. I'd have to do some, centroid location to figure out where the center of gravity of this complex assembly is. I'm lazy, okay? I don't want to do that. I'm old. Leave me alone. I would much rather, do my analysis about a fixed point, all right? I don't have to figure out where the center of gravity is if I do my analysis about the fixed point. It makes my life easy. So the only fixed point we have here is kind of the fixed point at the top of the pendulum, which is about which all of these points are spinning around. So let's go with that point. All right, so we'll do it about A. All right, away we go. General equation, summation of the angular momentum about point A, state number 1, plus the moments integrated over time equal angular momentum about point A, state number 2. Let's be clear, these moments about point A. All right. Away we go. Angular momentum about A in state number 1. Well, the only thing I really have to concern myself with in condition number 1 is the impending doom of this bullet. Doom of that particular guy. All right, that guy is, why does he keep jumping over there? I never really figured that out. All right, so this guy has a line of action that's purely horizontal. You can hopefully sort of see the line of action of the linear motion of this particular bullet. So if I'm interested in point A up here, and I want the angular momentum about point A, I want something like this position vector, which is the position vector R, which locates the bullet from A there, crossed with this component of the linear velocity. So if I'll write that out directly, I have to concern myself with the position vector, which locates B from A, crossed with the mass of the bullet times the velocity of bullet, state number 1. That's the only real thing I care about in condition number 1, is the angular motion associated with the linear motion of this bullet. Now, my impulses. Here, when cutting away the pin, we're going to have impulsive forces at the pin in the X and the Y directions. But since both of those guys travel right through point A here, there's no moment arm to those forces. And so the contribution to the impulsive moments from those particular forces is 0. So here we don't have any impulsive moments that we really have to care about. It's a strategic pick to do our conservation of momentum about A. Very strategic. I'm the strategicist. Now, complications when we go to angular momentum about point A in state number 2. Because we got 1, 2, 3, 4, 5 guys that we got to worry about. Just like my favorite burger chain, 5 guys. I'm just kidding. It's not my favorite burger chain. My favorite burger chain is McDonald's. Just kidding. Kind of. Let's do the easy ones first. We have the angular momentum of the disc and the angular momentum of the rod. So let's go straight away with those guys. Those guys are pretty easy. So here we're going to have something like, I'm going to try to be consistent with my notes here. So, mass moment of inertia at the center of gravity of the rod times the angular velocity. Here I'm just going to say angular velocity is one variable, because since everything's stuck together, everything has the same angular velocity. Okay, plus the mass moment of inertia of the disk times the angular velocity of the assembly. All right, so those are my 2 angular momentum components. Now I have to worry about the angular momentum associated with linear motion. let's first look at this guy. So he is located a distance away here, which is something like the position vector, which locates the center of gravity of the rod from A. All right, so this is the vector of interest here. So here we have the position vector, which locates the center of gravity of the rod from A, crossed with the velocity at the center of gravity of the rod times the mass of the rod. All right, so there you go with that particular guy. I'm going to add to that a similar looking term for the disk. All right, here's our linear velocity of the disk. Position vector, which locates the center of gravity of the disk from point A, crossed with the mass of the disk times the velocity of the disk in condition number 2. Try to keep my nomenclature the same. Mass of the rod, velocity of the rod, velocity at the center of gravity of the rod, state 2. Oh, so many variables. All right. Plus the position vector, which locates the bullet from A, crossed with the mass of the bullet times the velocity of the bullet, state number 2. All right. So there you go. Here's your full sort of generic general equation. Now, because the bullet and the rod and the disk are all connected together, we have kinematic relationships. Kinematics, rawr. All right. That is that the velocity magnitude at the center of gravity of the rod in state number 2 is simply equal to the magnitude of the position vector, which locates the center of gravity of the rod from point A, multiplied by the angular velocity omega. All right, V equals R omega, where this is kind of a bad G here. Or if you want to put this into a little bit easier terms to understand, the magnitude of the velocity of gravity center of the magnitude of the velocity at the center of gravity of the rod in condition number 2 is equal to the length between A and the center of gravity of the rod. So here is point A. Center of the gravity of the rod is here. So the distance here is 1 meter to the center of gravity of the rod. All right. So this is 1 meter times omega. V equals R omega. All right, we've seen this before. Conservation of energy. We've done this before. Conservation of momentum. Get the general idea. You'll have similar looking velocity at the center of gravity of the disk. State number 2 is equal to the length to the center of gravity of the disk from A multiplied by the angular velocity. Okay, so here we're going to have the magnitude of the velocity, the center of gravity of the disk, condition number 2, is equal to. Here, the distance between the center of gravity of the disk and point A. Okay, well, here's the center of gravity of the disk here. So this total length is 2.4 meters. Okay, so the length of the rod plus the radius of the disk get me 2.4 meters. Right. So my kinematic relationship here, 2.4 meters times omega. Last one, magnitude, the velocity of the bullet, state number 2, is equal to the position vector which locates the bullet from A, magnitude, multiplied by angular velocity. This one's tricky. All right. So the magnitude of the velocity of the bullet, state 2, is equal to the length of the vector which locates the bullet from point A. Okay. So that is this vector here. I've sort of drawn it before. That's this guy here, right? Which you will see has got a magnitude which is something like square root 2.4 squared plus 0.4 squared, right? We're relying on the right triangle here to get us that information, right? So 2.4 down, 0.4 to the left. That gets me the magnitude of the vector which locates the bullet from point A using Pythagorean theorem, square root 2.4 squared plus 0.4 squared. All right. Are you guys scared of the squared? You're scared of the squared. Don't be scared of the squared. Can you spare a square? All right, there you go. Now, with all our kinematics in place, we're ready. Back to this guy here. We go back to this guy. All right, so finally. Here we go, this particular term here. Position vector which locates the bullet from A crossed with the mass of the bullet times the velocity of the bullet in condition number 1. All right, so we're looking at the contribution here. All right, the distance to the line of action between A and my linear velocity of the bullet here is 2.4 meters, obviously. Okay, so this term is going to be something like 2.4 meters times the mass of the bullet, 0.01 kilograms times the velocity of bullet in condition number 1, given 800 meters per second. That's your first term. That's the angular momentum on the left-hand side. This is equal to, here I have the angular momentum term associated with the rod. So mass moment of inertia of a rod is 1/12 ml squared. So we are 1/12 the mass of the rod is 3 kilograms times the length of the rod, 2 meters squared. And don't forget your omega. So here, this is your IG of the rod, omega. All right. Instagram omega. Plus mass moment of inertia of the disk times the angular velocity of the disk. Here we have mass moment of inertia of a disk is 1/12 mr squared. So 1/12 the mass of the disk is 5 kilograms. The radius of the disk is 0.4 meters squared. Don't forget your omega. Instagram omega. Continuing. Now we add the first angular momentum component, which comes from linear motion. So we're going to here add this term, which comes from the linear motion here of the center of gravity of the rod. Okay, so the distance between point A and the center of gravity of the rod, that's 1 meter, multiplied by the mass of the rod, which is 3 kilograms, multiplied by the velocity at the center of gravity of the rod, which we're going to write in terms of omega, is 1 meter times omega. All right, and that comes from here. So this is something like R cross MV, right? All right, next term from the linear motion of the disk. Okay, so from point A to the center of gravity of the disk, that's 2.4 meters, multiplied by the mass of the disk, it's 5 kilograms, multiplied by the velocity at the center of gravity of the disk, which we're going to write in terms of the angular velocity of the disk, 2.4 meters times omega. Okay, so that is this term here. And then finally, the contribution from the bullet. All right, the distance between point A and the bullet we showed before. This is the square root of 2.4 squared plus 0.4 squared. This is meters. Multiplied by the mass of the bullet, 0.01 kilograms, times the velocity of the bullet, written in terms of the angular velocity of the system, which again has this kinematic relationship that uses the length between A and the bullet, which is 2.4 squared plus 0.4 squared. All this multiplied by omega. So there you go. There's your full conservation of angular momentum equation, with the only variable being the variable of interest, this angular velocity omega. Complicated. God damn. Got multiple objects. We've got angular momentum, we've got linear momentum, all contributing to angular momentum. We've got kinematics here relating the centers of gravity's velocity to angular momentum of the system. Man, I'm old. Leave me alone. It's complicated. Let's look at each one of these terms individually. So I think it's interesting to look at the various terms and look at their relative contributions. So this left-hand side, let's just multiply that out and look at what the value is. So left-hand side there, you're going to end up with something like 19.2 Newton meter seconds. My favorite units, Newton meter seconds. All right. Equal to the right-hand side here, this first term, remember, looked something like Instagram omega of the rod. All right, so we multiply all those things out. 1 on 12 times 3 times 2 squared. Well, that's just going to end us up with 1 omega, or I'll just write omega here. The next term, which is Instagram omega of the disk, this is going to get us with 1/2 times 5 times 0.4 squared, or if you multiply that out, you get 0.4 omega. We're going to add to that contribution from this guy, which I can do that one in my head. It's going to be 3 omega. I like when you multiply by 1. That's easy. What's even more easy is multiplying by 0. So easy. Caveman can do it. All right. Next, we have the contribution of the linear motion of the disk to angular momentum. All right. Here's our biggest contributor. It is the oil industry of contributions. Oh, God, that's a complicated joke. Right, 28.8 omega. And then the last contribution we have to worry about is all this associated with the contribution of the bullet. And here that contribution is plus 0.06 omega. So it's nice to just see the relative contributions of each of these guys. Here, this is from Ig omega of the rod. This is from Ig omega of the disk. This here is from R cross mv of the disk, of the rod. This here is from R cross mv of the disk. This here is from R cross mv of the bullet. All right. So it's interesting to look at the relative contributions of all of these terms. I mean, the one that blows the rest of them away is the contribution that's coming from the linear motion of the disk. All right, that's this guy here. It's like blowing away the rest of them. It's 10 times more than that one, which is the next highest. All right, so this is the main contributing. Contributor. It's the oil industry of the lobbyist group. All right, it's the main contributor. He gets all the attention. All right. So interesting to see. The contribution of the bullet after it's been embedded in the system, relatively low. All right, so you see after the bullet gets stuck in, it's not really contributing much. The coefficient leading that particular term is very low, 0.06. And well, that's just because the mass of the bullet generally is very low. So its general contribution to the angular momentum is going to be low just because it has low mass. All right, so that's the idea there. If you wanted to neglect this term and make some engineering judgment there, I'm cool with that, but you gotta at least show me some verification of neglecting that term. I mean, when you say this is can I do math in my head, 0.2% of this value here, then you can just say, yeah, okay, that 28.8 is he's dominating rar. All right, so anyway, enough of that. Final answer, if you include all contributions of all pieces, looks something like 0.58 radians per second. There you go. There's your conservation of momentum problem. Hopefully that's jiving some memories. You're shaking off the rust. You're sort of understanding these compound terms, angular momentum, linear momentum, how they both contribute to the overall general conservation of momentum of the system. Okay, so that's it for today. I'll do some more practice problems tomorrow where we're looking at linkages and gears, and then your test is on Thursday. So that's it. Thanks for coming. Hopefully see you guys tomorrow.